All right, so everyone, welcome to the Zero Knowledge Workshop. So my name is Marco. I'm a researcher at QuantStamp. We're a security and blockchain research company. I'm also studying computer science here. Some of the research interests that I have are in zero knowledge, blockchains, and cryptography. This workshop is not going to be so much a research-heavy or academic introduction, but more so an introduction to how to actually build zero knowledge proofs. Because many of you who are here are going to be interested in building a project this weekend or are already building one. And I want to show you how you can easily get started with building ZK directly into your application. In fact, the app that we'll be building today will be based on the web. So any of you who are building a web application of any sort should be able to, out the box, start using the tools I'm going to give you, and it'll work hopefully pretty nicely. Great. So before we actually get into the tutorial and building, I'd like to start with a bit of a conceptual understanding of zero knowledge. So who here has actually heard of zero knowledge before? Decent amount of people, maybe half. That's pretty good. So what I would like to do is kind of walk through two examples. One of them is going to be more of a puzzle of sort, and the second one is going to be kind of more of like a real life situation. And then after that, we'll get right into the tutorial. I already kind of covered this, so I'm not going to go over that. So the first example I want to talk about, and maybe you guys have seen this before if you are more familiar with zero knowledge, is this idea of Waldo. So how many of you have played this game, Where's Waldo, before? Okay, good. So we're going to play Where's Waldo. And the way this is going to work is I would like one of you, and this is actually a very easy puzzle on purpose, but I would like one of you to tell me where Waldo is, but there's a catch to this. I want you to not spoil the solution for the rest of your peers here. Can anyone do that for me? Or anyone want to volunteer maybe? Or has any idea about how we would do that?
I think the hypothetical here is usually you could get like a great big piece of cardboard,
and then
you can put a hole in it, and then you can put the picture behind it, and you can show where Waldo is, but it's hard to tell where they would be in the picture if you did not have the card.
Yes, what's your name?
I'm sorry.
Simon. We were in a class together last year, I'm pretty sure. Anyways, yeah, Simon is correct here, and I'm going to demonstrate that in a moment. Does anyone want to actually just first point out where Waldo is? Has anyone seen it? Okay, great. So actually, I'll show you right now. Waldo is here. And this example is exactly what Simon just pointed out. We were kind of just covering the picture. Now, this isn't a very good way of not spoiling the answer because the image itself is kind of centered, and we can see that the cardboard kind of covers the entire puzzle. So all of you now know where Waldo is, and I kind of spoiled it for you. So this wasn't very good. But this is kind of the notion that we're going to get at in terms of zero knowledge. We want to kind of convince some verifier, and this is the language I'm going to use. We're going to use a prover, me being the prover and you being the verifier. I want to convince you, the verifier, that I indeed had to have known some position of Waldo without having to actually reveal I want to reveal as little information as possible. That's kind of what we're getting at. And as such, you shouldn't even be able to find Waldo yourself. You should just be convinced that that I had to have known a location for Waldo. A better way to have done this would have been to obfuscate the image a bit more. So like we kind of just move the image around a bit and then make the cardboard a lot larger. And now if I told you, you know, I know where Waldo is. I indeed do know where Waldo is because, well, he's right there. And I just snipped him there. But you don't really gain any information about the original picture. So if I went back to here and I asked you find him, like the image that I just showed you doesn't really help you too much. You could argue something about like how you can kind of see the limbs maybe, but like suppose that we had a better cropped image, then you don't really gain any information whatsoever. Okay, so that's Waldo, and these are actually, believe it or not, very applicable to the real world. The second example that I want to cover is that of biometric data, even passwords, any sort of authentication really. So who here has an iPhone or actually Touch ID on their phone? That's what I want to get. Who here uses Face ID? Okay, so pretty much all of you. I would like to start off by saying that we're putting, by using Touch ID and Face ID, we're kind of putting a lot of trust into the companies that we are interacting with. Like Apple pretty much has all information, and Google and all these other companies. And if we were trying to design a protocol in which we wanted to use Face ID or Touch ID, but without compromising the privacy, it would be quite difficult. And the model that I'm going to show you today kind of demonstrates how we maybe do that using zero knowledge. So in a typical model, you might have something along the lines of this. Goose here, who wants to authenticate using their phone or any sort of authentication abstractly, is going to send some data to some server or some endpoint or whatever it is. And this server, this backend, is going to take this information and is going to take a hash function. It's going to check the hash against some hash that's located on a database somewhere, or some variation of this. Is very oversimplified. But and then what's going to happen is that the server is going to spit back a response to the client here, to Mr. Goose, is in fact verified. So, you know, when you check your phone here, it's going to, well, in the case of the phone, it's local, but maybe, for example, you're walking through an airport and there's a kiosk for Nexus, which checks your face. And then that way, a user or some backend, in this case, well, the government, is going to check your face and verify whether or not you are indeed qualified to enter. So these kind of systems in general are very good for zero knowledge in terms of applying some privacy techniques. Now, obviously, there's a bit of a divide here, and I just want to point this out quickly. That is, designing systems that are private in nature or that preserve privacy for our users is kind of a utopian thing, because in practice, you know, there's like implications, and a lot of governments and organizations don't really have an incentive to do that. But let's suppose, just for like the remaining of this lecture, that we are interested in making our users maintain their privacy. So how would we do that? Actually, does anyone have any ideas of how we would do that? First of all, applying the same principles from Waldo maybe to this flow here. If not, that's fine. I'm going to show you. So let's maybe walk through a bit more detail. What exactly are the problems with this model that I just showed you? So first thing first, Goose's data is stored on some server. We're going to show that we can kind of mitigate this. Maybe we can't entirely remove that problem. Goose can be uniquely identified. So suppose that this example the government told you about earlier, right? We have some hash version or some type of process version of your face, basically, on some server somewhere, some database. If the government wanted to, and they were trying to perform some sort of surveillance, or any organization for that matter, they could potentially use that to identify you, or in a more abstract sense, they could adversely use that information. Another problem with this model is that Goose is kind of susceptible to man in the middle. So just show you, at some point, Goose has to kind of rely on their sensitive data being transmitted from their device or from a kiosk or from any sort of like scanner for that matter to some server. And in between that, if the channel is compromised or the actual hardware itself is compromised, there might be some complications there, and Goose might get his private data leaked. So those are the three kind of issues, and we're going to address these three using zero knowledge. So sorry for the image being a little bit small. I'll get to that in a second. But kind of what we're going to do is add a layer of abstraction on top of what the previous model has. So instead of just sending the data directly to the server or to the and doing a database check, we want the Goose to perform a proof generation. So what that actually means is that instead of providing the direct data, Goose is going to take their device or some kiosk or some other type of hardware, and this device is going to look at Goose, and instead of just sending the data, it's going to generate a proof. And this proof is going to replace this data completely for our purposes. So then Goose is going to take their data, and they're going to send it still to a server. So the server, what the server is going to do now is they're going to have a verifier on that end, and the verifier is going to accept this proof, and then with this proof, then the server will spit out a yes or a no. This part up here is something called a Merkle tree, and I'm going to kind of just omit that in terms of for time now. But just know that when we're designing zero knowledge systems or systems that try to preserve privacy, we will often incorporate other kind of cryptographic tools or like data structure tools. A Merkle tree is one of them. I encourage you to like look it up after, but just know that like commonly when you're using a zero knowledge system, this data structure, this Merkle tree will be incorporated. So just keep that in mind for now. Okay, so how did we address these three issues with the model I just demonstrated? So the first things first is that although we are still storing some level of data at the Merkle tree, what we have done now is we've replaced the direct check with the hash with the verifier. So now all the server has to do is just take in a proof, and then I'm going to check this proof, and if it's valid in the sense that in the sense that I will define later, then we're good. So Goose can scan their phone and verify themselves to some entity, some organization, some government, some company, whatever it may be. The second thing is that Goose can no longer really be uniquely identified because the way we've changed the structure, we're not going to store some data that can be easily that we can easily check against. I know that sounds a little bit complicated, but what I really mean is that instead of having to rely on the government to not be able to, survey people and just check data that they collect, the user now has to generate a proof of some sort, and this proof doesn't really reveal any information about the person. So we've kind of solved that issue. And the third thing is that man in the middle, if a person is compromised the system and has able to retrieve the proof that the user has sent to the server, they can't really do much with that proof. It doesn't really tell anything about the user data. So in a sense, we kind of solve all these three issues. And for the more experienced people in the audience, there's a lot of caveats there. But generally speaking, you can approach a private or privacy-preserving system that maintains mostly these properties by using zero knowledge. So I would just I like to say that it's not perfect and it's far from perfect, but this is kind of the approach that we want to take. Okay, so how does this actually generalize? At this point, I haven't actually even given you really like a simple definition of zero knowledge or some type of definition at all. And at this point, I've just given you only two examples. So I will do that now. I'll give you some definition. Zero knowledge proofs allow one user or party to demonstrate to another party that a particular statement is true without revealing any information beyond the validity of the statement itself. So this is kind of the generalization that we were working towards, and it's very powerful. If I wanted to prove to you that I was above a certain age, but I didn't want to tell you my exact age, I could do this with using zero knowledge proofs. If I wanted to perform a credit check and tell you that I qualify for some loan, but I didn't want to actually reveal my credit score, I could use zero knowledge proofs. If I want to do any authentication with passwords or biometrics, and I don't want to compromise my information, then zero knowledge proofs would be applied to this situation. So already what we can see is that it's a very powerful primitive. And there's a lot of limitations in the current state of the art regarding efficiency and making it accessible, like the tooling. But I'm personally hopeful that we will solve most of these issues in the next 5 to 10 years or so. And I think that because it's so powerful for privacy, that it will be a staple primitive for pretty much our whole society. Great. So another way you can kind of think of this is like ZK as like a shield. So if yellow goose and purple goose are trying to send messages to each other and they're trying to communicate, it's really hard to tell who yellow goose is talking to, whether they're talking to the pink goose or the purple goose, or whether their information is even compromised by a man in the middle. So by applying zero knowledge techniques, we can kind of eliminate or hope at least to eliminate a lot of these concerns. And that's kind of the way I would think about it. There's actually a few new, in the past couple of years, other interesting applications that aren't only just privacy-based. I will quickly just mention one. In the case of, maybe if we're familiar more with blockchains and such, zero-knowledge rollups. Basically, we can use zero knowledge to save some computation and perform computation off-chain instead of having to do it on-chain. And there's just a plethora of other examples like this. But privacy is kind of the main one that for us who are learning can kind of model zero knowledge and use it to build applications. Okay, so now that we kind of covered the intuition, actually we'll take a quick second. Does anyone have any questions at all? I went through that really fast about any of the information that I just went through. Yes?
Can you just do the Really quick, given what we just talked about the video.
I don't have time for that. I'm really, really sorry. But I think there'll be a recording and slides posted after. Really, really sorry, but yeah, I just don't have time for that. Any other questions? Yes.
Hash-based password
Yes.
password authentication. Like for example, when I store password as a hash.
Yep.
Authenticate the user. I'm just gonna try the hash value of what we actually have the value stored. Is that
So in the case of that, what you could do is you could have a zero knowledge that verify or zero knowledge proof that verifies that I know the pre-image of a hash. So that's how you would apply that to that case. So like I can have and I'll show this in a second, but I could build a circuit that just basically shows that I know the pre-image isn't hash, and then you can store the hash of the password on your server. Yeah. Okay. Yeah. So how do we actually build ZK proofs? That's the focus of this talk, and I really want you guys to all walk away today being able to actually integrate zero knowledge directly into your application. That is my goal. So before we get into the tutorial, there's just only a couple terms that I want to go over quickly. The first term I'd like to cover is a ZK snark. So ZK snark, for our intents and purposes, is basically just a form of zero knowledge proof. And particularly this form is succinct in nature, meaning that it is quick and easy, or short and quick to verify, and non-interactive, meaning that there is not multiple rounds of communication between the prover and the verifier. The second thing I want to go over is this thing called CIRCOM. CIRCOM is a domain-specific language. It is the language that we will use to build ZK snarks. And remember, ZK snarks is kind of, for our intents and purposes, the practical way that we will implement zero knowledge. The third thing is constraints, and this isn't like a zero knowledge like specific term per se, but when we're talking about zero knowledge and we're trying to build systems that integrate zero knowledge, we always have to think about constraints. Like what kind of invariants does our system have that must hold? What kind of things are really important to our system? It's critical that we actually get our constraints right when we're building a proof or zero knowledge proof, because if we don't, then there might be a hole somewhere in our system. And if there's a hole in our system, then it's no good anyways. So really important that when we're translating from the real world constraints to a system of some sort, that we maintain the same constraints. All right, so tutorial time. What we're going to be building today is this. Does anyone know what this is? It's Magic Square. Yeah, I think someone said it. So it's quite popular. It's probably done leak code problems with it before. And basically, we're going to build a web application that implements proofs of the Magic Square. Specifically, we can prove that we know 9 inputs such that the Magic Square properties hold. Now, there are 3 constraints or properties that the Magic Square has that we're interested in. Can anyone tell me one of those properties? Not a trick question, I promise. Yep. It has to be, yes, in this case, 15. Like each diagonal row and column has to sum to 15. There's 2 more properties I want to highlight, and they're simple, but I really want to stress how important it is that we like kind of make that observation. Does anyone have any idea what the second? Yep.
they can't be repeated?
Yes, they have to be unique. Perfect. One more property that we're interested in. Any volunteers? Okay, I will just tell you. The last property is that the numbers have to be 1 and 9 inclusive. So we can't have 10 or some other random number. For this instance, where we're interested in 15. They're distinct. They have the same sum, the magic number, and they also are between 1 and 9 in this case. For this particular instance of the problem. Yeah, great. Okay, so we're going to build that, and here are the properties again just listed for your convenience. Cool. So I'm going to just switch my screen now to, I have to do this in the Google Meet first, to my code, and then we're going to build it. So, I don't think it lets me. Okay, I'll just share my entire screen then. Oh, well. Okay, great. So who here is actually going to try and build along? Just want to get a sense for pacing and stuff. You can find the, actually, maybe I'll just give it minutes. If you guys are interested in like actually building this app, which I like really encourage you to do, there is a GitHub link. It should be in the hack pack or somewhere available wherever you're viewing on your screens. I will just give a minute for people to pull that up. And then once you have the GitHub pulled up, just go to or just clone the repository and then switch to the exercise branch. Is everyone like familiar with like how to do that roughly? Okay. Give like 30 more seconds. By the way, this tutorial building this app should work for Mac, Linux. I haven't tested it in Windows, but in theory, it should also work for Windows. And I'm assuming if you're doing this type of stuff on Windows, that you know the typical like nuances that comes with that. So I wouldn't ever recommend developing Windows though. Does anyone need more time, or we're good? Okay, I'll just assume then that we're good. So yeah, if you have the repository pulled up and you cloned it and you switch to the exercise branch, you will basically be exactly where I am here. And I'll make this a little bit bigger. Is it? Oh, I don't want that. You guys see this? Is this good? Yeah. Okay. So we're gonna be filling in this part. Let me actually first explain what's happening here a bit because it's kind of a big repo. Okay, so I've kind of shielded you guys away from a lot of the complications that comes with building zero knowledge. I will admit that the tooling and the developer experience isn't as nice as I'd like it to be at this point in the state of the art. But what we will do is we will focus on just this one file here. And this file, this magic underscore square.circom file is what we're going to be coding in. This is the file that we're going to basically take the magic square problem, which I showed you earlier, and we're going to convert it into some, for our purposes, computer program that can then be used to generate a zero knowledge proof. So what we're actually doing is something called building a circuit, which this circuit is an arithmetic circuit, which is a representation of the original problem. And whenever you are building like building zero knowledge proofs, you are basically taking some type of problem, some problem in MP specifically, and you are trying to convert it into an arithmetic circuit. Arithmetic circuits are very convenient because we can basically, like I said, represent any problem in them, and then we can actually easily generate a proof from it. It's very easy, and we can do it deterministically. So what you're going to do before we actually build this file, if you haven't done so already, there's a bash file here, setup.sh. Just run this file. And what this file will do is you can check it, but it will install some dependencies if you don't have them, like Rust, Circom, and it will also install the node dependencies and some other things too. You basically need that in order to actually compile the circuit we're going to do in a second. And then after that, well, I'll start getting into the actual code itself. So this program is actually going to be very simple. It's going to have basically kind of 4 parts. Part 1 is just the simple inputs and the like setup. Part 2 part 2 to 4 is just going to be the constraints. We're going to do constraint by constraint by constraint. So the first thing I will do is I'll define some inputs. So when we're working in Circom, and by the way, like I said, Circom is a DSL. It's kind of similar to C in terms of syntax. There's only like a few weird things like this arrow, which I'll explain in a second. But when we're defining inputs to our program, we're going to use signal inputs and then the variable name. And then we're going to just kind of actually repeat this 9 times. So I'm sorry for the redundancy here. Maybe there could have been a cleverer way to do it, but this is pretty simple for our purposes. So we're just going to basically create some inputs for all of the different spots on the grid. It's exactly what you would expect. There should be 2, 1, I'm sorry. 2, 2, 2, 3. And then these ones will go 3, 1, 3, 2, and then 3, 3. Great. So now we have our inputs. Pretty simple so far. We're also going to define there's an output variable, signal outputs results. And I actually am not going to talk about the results right now, but like just know that that thing exists, and we're going to just kind of keep that away. So like ignore below this. Sorry, for now. Yeah, now that we have our inputs, we are ready to kind of move on to our first constraint. So who can remember what the first kind of big property was that we want to enforce? And go ahead.
And it's between 1 and 9.
Yes, that's one of them. The first one that we really care about, like the kind of the yes, exactly. The most important property is the sum here, and so that's kind of what we'll enforce. So we'll go signal cells 9. This is going to create a new array, and we're going to just input all these variables into an array. The reason why we're kind of doing this redundancy is because it's going to help us check this property, the sum, in a second, so we don't have to do it completely manually. So we'll just do this here. So, oh, sorry. Okay, so this syntax here with the arrow, by the way, means that you're feeding this value of A1, for example, A11, for example, into the first index of this list cell. And it also enforces that they have to be equal. Because in CIRCOM, we use triple equal for constraints, equality constraints. Yeah. And then, yeah, we're going to just do this a bunch of times. So I'm just going to paste this, and you can just follow along this. And then just replace all these numbers here, like so. 1, 2, 3, 4. Need one more. 8. Then we have to also replace we have to replace these as well. 2, 1. That's yes, code's being annoying. 2, 2. 2. A2, 3. A2, A3, 1. Okay. Yeah. So we have all of our values into an array now, and then what we're going to do is then check that the columns, rows, diagonals all sum to 15. So then the way we'll do that is basically we can check directly the cells. So we'll just go. Well, actually, what I'll do first is I'll define a variable called sum rows, which takes in 3 values. And we'll do some diags, which also takes in 3 values. And then we'll do some columns, which also takes in 3 values. And then we're going to input those values that we saw earlier directly into these. So we'll go A11 plus A12 plus A3. Some columns is going to take in some columns should take in, oh, sorry, hold on. I need to, give me 1 second here. I had this program designed in a very specific way, and then the way I was thinking about it in my head right now was different than the way I originally wrote it. So I just want to maintain consistency with what's on the solution. Sorry about that. Okay. Yeah. Okay. So the way I did it was actually this way. So we'll actually define 3 of these here. One more, and then a third one. And then for this one, we'll go 2, 1, 2, 2, and then 2, 3. And then for this one, we'll go 3, 1, 3, 2, 3, 3. And this is our sum for our rows. Now we'll do the sum for columns, which is going to be this variable earlier. It's a similar thing. A11 plus A21 plus A31. And then we'll repeat that 2 more times. And then the diagonal one's only going to be 1 line, so that's pretty short at least. It should be 0. 2. Okay, 2, 2, 2, 2, 3, 2. And then the columns here is 1, 3, 2, 3, and 3, 3. And then our diagonals, sum diags 0 should just be equal to a11 plus a22 plus a33. And I also forgot semicolons here. Didn't forget any other ones. Cool. Okay. So at this point, oh, there's also one more sum diag actually. Sum diags 1. Forgot about the other diagonal. A13 plus A22 plus A31. This. Okay, so now that we've actually instantiated all of these variables, we're ready to actually do the check. So we'll go for var I equals 0, I less than 9, I less than 3. Sorry, we're checking those 3, and then I plus plus. We will enforce that some rows I going to be equal to exactly 15, and some columns I is going to be exactly 15 as well. And then we'll do one more check for the diagonals. So for var I equals 0, I is less than 2, I plus plus. Some diagonals of I is going to be exactly 15 as well. And there should be something else here. Okay. So that's basically it for the first, yes.
For the subgroup column, the bit indexes should be 0, 1, 2.
For which one? Oh, you mean that? Yes. Thank you for pointing out. Thank you. Coding it live is always a bit of a stress. Yeah. Thank you for pointing that out. Yeah. So we've done the first constraint. So this actually just kind of tells us like, okay, all these different values are going to be exactly 15. So we're good so far. Now we're going to work on the second constraint. The second constraint is going to be my notes here. We do the uniqueness one next. Okay. So we will check uniqueness. There's a bunch of different ways that you could check uniqueness here. I'm going to quickly just like gloss over different ways you could do it because it kind of matters here actually. Can anyone give me like a suggestion actually? What's one way that we could check uniqueness of the 9 numbers? Again, not a trick question. Yeah.
For each number, check that it's not equal.
Like a pairwise check, right? Yeah. That's one way we could do it. In this case, it's not too bad if we're doing that because it's 9 choose 2, which is like constant in this case. But if we're doing it with large numbers of n, it might be pretty inefficient. In classical like sense, at least, maybe not here. And I'll explain why in a second. And another way we could do it is we could take the arrays, put it into it, or we have our cells array. We could sort that and then just check numbers 1 to 9 that the index is equal to the corresponding I. Like that's one way we could do it. Another way we could do is we could take the array and then we could like hash that, like the sorted array from 1 to 9, and then check that the sorted array is equal, the hashes are equal. That one kind of seems a little bit redundant because we're still doing sorting, but actually so doing these hashing operations in CIRCOM is sometimes nice because one issue that we have with like when we're building circuits is that whenever we're using sorting or some type of like algorithm that uses a lot of like constraint checks, it actually blows up the complexity of our circuit. So these circuits can actually be very inefficient. Some of the stuff that I work on takes like 6 hours to compile into a proof. And by the way, this is on like a 32 gigabyte and with the NVIDIA 4070, like that type of machine, right? So these ones will not be like that. These ones will be like a second. But when we're building our circuits and we're thinking about real life problems and we're working with like scalable, like n-sized parameters, we want to reduce the amount of equality constraints as much as possible, because every time we introduce some new equality constraints or like it increases with the order of the input, we have to enforce that in the proof. And again, I'm kind of black boxing a lot of this here, not really explaining why that's the case, but it just so happens to be that the complexity will blow up. So the second constraint, of these three different ways I kind of described it, I'm just going to use the pairwise check because it's kind of simple for us right now to do that. And there's a lot of other complications I want to avoid in terms of sorting. So we'll just go for all the different numbers, I is less than 9. And then we'll do another loop here for their j. Typically, you want to use the triple sign equality whenever you can. That's the most like conventional way in CIRCOM, I guess. But sometimes certain constraints or like certain equality checks that you're trying to do, it's easier to just use the assert, which is exactly the same as you expect in like C or something like that. We're just going to check that cells of I minus cells of J is not equal to 0. And the reason why we do it specifically that is just that's kind of the CIRCOM convention, how we write our asserts. That's basically our second constraint. And actually, our third constraint, I'm going to do it inside the loop here because this just is very convenient. So we're going to check that, check this constraint here. Basically, the number is between 1 and 9 inclusive. Okay, so we'll just do assert that cells I is greater or equal to 1 and assert that cells J is less than or equal to 9. And that's actually it in terms of the circuit. So we've done all the 3 goals that we originally outlined. We've enforced that the diagonals, columns, rows all sum to 15, and we've informed uniqueness property, and we've enforced the range. So that's pretty much it for the circuit. I'm just making sure I didn't make any syntax errors or something. To be honest, I'll be surprised if I did it perfectly the first time without doing something. I'm going to actually define one more variable here. I'm not going to explain why it has to do with the output. Again, I'm kind of just ignoring that part for now. I can talk about it after if there's questions. And looks good to me. So, okay, what should happen now, and you guys following along can do. Oh, sorry, yes.
And then everything after says cells.
Thank you. You guys are my debuggers. Yes. You saved me a headache there from doing that live too, finding that. Yeah, it's just trying to explain it while write it, it's sometimes a little bit hard. Yeah, okay. So what we're going to do now, again, for those following along, there's a bash script that I put in the exercise branch. It's called compile.sh. And we're just going to run that. And everything, if I didn't mess up this code here, should work out the box perfectly. We'll find out in a second here. Hey, yeah, as expected. I might have not. Did I use 72? It isn't like yeah, okay, thank you. Okay, second try, not too bad. I've seen worse. So it compiled, and it also did a bunch of other little magic things that I've kind of again moved away out of this workshop for your purposes. And our circuit has compiled and generated a few files, and I've also moved these files into the right locations for our app. So now all we have to do is cd into magic square, and then we just npm start. And I might have to change. Oh, actually, I'm showing my whole screen, so it's fine. It doesn't have a React script apparently. I have to React scripts. React scripts. npm change the best fix. I think I just had the npm installed because I didn't run the file that I gave you guys actually earlier because I had most of the dependencies installed. Okay, now let's try again. So we just run this and yeah, okay, cool. Should open in the browser in a second. Perfect. Okay, cool. So sorry for the not great UI. I'm not a designer. But basically what we should be able to do now is input numbers 1 to 9 in this grid here, and it's going to generate proof, and it will also verify the proof in the browser. I would like to stress though that when you're building your own applications, you can take this verifier code and it's in the repo, and you can just move it to a backend if you like. It doesn't have to be in the browser. I just did it in the browser just for convenience. So how do you run it? You just cd into the Magic Square directory, and then you just npm start. It's just a simple React app. Press pick in VS Code? Is that what you mean? Sorry. However you normally, I'm not familiar with your environment, but however you normally run React apps, the exact same thing should work here. Yes. So I don't have this Magic Square memorized. So I'm just gonna check here, 951, 438. And if we wrote the circuit correctly, this should spit back okay or some variation of that. I didn't write it good. 438, 951, 276. What I'll do, okay, I might have made a mistake when I typed it in. Sorry for this cop out, but I'm just gonna go here to my solution, which you can find in the repository. And I'm just gonna paste this in here and then just recompile it. Yeah, sorry for the cop out, but I just sometimes make you errors like that. And then we just do this again. SH. Okay, and then we can cd into Magic Square again and try again. Two, 7, 6, 9, 5, 1, 4, 3, 8. Oh. 7, 6. 6 there. 1, 5, 1. Okay, so that worked. I made an error somewhere in the code. It's an exercise to find where it was. But yes, so that's kind of what I wanted to show you guys for this application. The actual code, like what's happening, I'll maybe quickly show you. If I go to this file here, all that's happening, it's like the React part is actually surprisingly simple. We just take inputs from our front end, and then we just invoke this library called Snark.js. Comes from ZK Snark. And we just have these files that are generated from the circuit that I just showed you right now. And these files that get compiled and moved to the right location. And then it generates a proof just from those two files. Then this code takes that proof, and then it just checks this handle verify function, which just also invokes Snark.js, which will just check that the proof is valid. And again, it's all black box. I didn't really explain like how that works. Maybe if you're interested, I'd love to tell you about it after. But that's kind of it in terms of the tutorial. Are there any questions about like anything of the development process here? Yes.
One of the things you're saying about this is like the examples you were giving, like proving a credit score or something like that. They're all like they're interfacing real world things.
Yes.
And like, how is that possible? Like the information has to be stored somewhere.
Well, in this case, for example, right, what would happen is like, suppose I use this app on my device, on my phone, and I just put my 9 numbers in. I will contest that in the browser, in that specific session of the browser, before you click the button, the data just disappears. Yes, if someone had access to your client and to your browser and is able to monitor your browser while you input the numbers, they can still steal your information. But what's really happening here is that once those 9 numbers go in, it goes into our proof system, which we just, it goes into these 2 files right here, this WASM file and the ZKey file. in and then they're gone. And then once this proof that is generated gets sent to the verifier, none of the original information about the 9 numbers is retrievable for the verifier. That is gone forever. Forever, like up to like a really like small probability, actually. But yeah. Does that make sense? I'm not sure if I answered. Cool. Yeah. What these come from when you run the compile script. The compile script just does the compilation. It also moves things around. Are there any other questions about this? Are you able to get the work? I can troubleshoot it after maybe 2. I'm pretty much done this here. So I think that's it. If no one has any further questions about zero knowledge in general, if you have if you're interested and I've piqued your interest in this, I can again chat more deep about like the math or like what's actually happening here, or like how you can get to work in your own app if you want to try and use zero knowledge. But otherwise, I'm done with this workshop. Thank you all for coming, and I really appreciate your time.